Hello everyone. In this session, we are going to study the nuclear reactions in stars. But first of all, let's review atom. Atom is composed of the two components of the electron and the nucleus. Electron is located around the nucleus. The size of the atom is about 10 to minus 8 centimeters. And the nucleus is much smaller than the atoms, so it becomes 10 to minus 12 centimeters. And nucleus is composed of the proton and the neutrons. And the protons is about 10 to minus 13 centimeters. And the proton is composed of the quark, 3 quarks, up quark and down quark. Charge of the up quark is a positive 2 over 3e charge unit. Then size is a 10 to minus 16 centimeters. So elementary particle in physics we use is a quark and leptons. So as I explained, a proton is composed of the 2 up quarks and 1 down quark. We have 6 quarks: up quark, down quark, charm quark, strange quark, top quark, and bottom quark. Gell-Mann received the Nobel Prize in Physics in 1969 because he proposed the existence of the quarks. And the light particle we call the lepton, electron, muon, and the tau, electron neutrinos, and the muon neutrinos, and the tau neutrinos. These are elementary particles we consider in physics. And also we need to consider the antiparticles. Each particle has antiparticles. For the electrons, we have an antiparticle of the electrons. Antiparticle of the electron has the same mass with the electron. But the charge is opposite. Electron has a negative charge, so antiparticle of the electron has a positive charge. Magnitude of the charge is exactly the same. So for the electrons, antiparticle of the electron we call the positron. Positron was discovered in 1932 by the Anderson, and because of this discovery, he won the Nobel Prize. Each elementary particle has antiparticles. We are going to study the nuclear reactions happening inside of the stars. Stars lose energy by emission of radiation, emission of photons. Photon is escaping from the surface of our stars and losing the energies. So by losing the energy, star is going to evolve. So energy actually is produced by the nuclear reactions. So this is a typical case of the nuclear reactions. So I and J is a reactant. I react with a J to produce the two products of the K and L. Reactant of I has a mass number of A sub I and the charge number of the G sub I. Reactant J has a mass number is A sub J and the charge number G sub J. And react to produce the product is K has a sub K and the G sub K. And L has a sub L and the G sub L. And during the reaction, charge number is conserved. So sum of the G sub I and the G sub J is equal to the G sub K plus G sub L. So charge number have to be conserved. But mass is not conserved. So this is a source of the energy produced in the nuclear reactions. Mass is a form of the energy by using the famous equation of the E equal mc squares. By changing the mass between the product and the reactant, energy is produced. So how much energy is produced we could calculate by calculating the change of the masses. So amount of the energy is released can be calculated. M sub I plus M sub J is the mass of the reactant minus mass of the product, M sub K, M sub L, times C squares. So change of the mass times C squares give us the total amount of the energies produced in the nuclear reactions. it's better to introduce the atomic mass unit. Atomic mass unit is defined by this equation. M sub h does not mean the protons. M sub h is this definitions. Mass of the carbon 12 divided by the 12. So M sub h expressed 1.66 times 10 to minus 27 kilograms. This is important. Atomic mass unit is very close to the mass of protons, but it's not the mass of the protons. Very close, but not the mass of the protons. When you try to calculate amount of the energies produced in the nuclear reactions, we often express the mass excess. Amount of the energy released is a difference of the masses of the reactant to the mass of the product. So M sub I plus M sub j minus M sub k minus M sub L c squares. Each term is a subtract A sub I M sub h. So M sub h is the atomic mass unit times the mass number A sub I. So we call that this is a mass excess. So delta M sub I is expressed M sub I minus A sub I M sub h c squares. So if you write down the equation of the Q sub ij case, so each term is M sub I minus A sub I M sub h, M sub j minus A sub j M sub h, minus M sub k minus A sub k M sub h, M sub L A sub L M sub h. By subtracting these quantities, you have to add these quantities here. Actually, the mass number is conserved. Each term, M sub I minus A sub I M sub h. This is gonna be delta Mi. This is using the mass excess. This is delta Mj minus delta Mk delta Ml. So each mass excess, you can look at the database. For example, in the case of the helium-4, it becomes mass excess of the helium-4 is a 2.425 mega electron volt. For the protons, as I explained, the proton is not equal to the atomic mass unit. So we have a delta MP. Proton has a 7.289 mega electron volt. So when you want to calculate energies produced in nuclear reactions, you can draw this type of the graph. So we'd like to find out how much energy is produced by the nuclear reactions for the proton reacts to the proton to produce the helium-4. In this case, we have 4 protons. Mass excess is a difference from the atomic mass unit, M sub h. So this difference can be calculated. Single delta MP, this is delta MP, is 7.2 mega electron volt. Times 4 becomes 29.156 mega electron volt. You can calculate these numbers using the mass excess of protons. Also, heliums-4, we have mass excess of the heliums. It's gonna be 2.425 from the mass excess of the delta M helium-4. We have these two data. From these data, you can calculate the produced energies. So you can calculate the difference of the two energy of the delta MP and the delta M helium-4. So these numbers you can calculate. So 26.731 mega electron volt of the energy is produced by these nuclear reactions. So if you find the mass excess of each reactant and the product, then you could calculate how much energy is produced by the nuclear reactions. Okay, this is the end of this session.